Assalamu alaikum dear students. This is lecture 10C of week 5. This lecture is in the continuation of lecture 10A and B, in which we were covering the high frequency response of BJT amplifier from chapter 9 of the book Electronic Devices and Circuit by Lustert. So we are working at high frequency response of BJT amplifier, and today's topic is gain bandwidth product. In high frequency response, we already computed the cutoff frequencies associated with the parasitic capacitances, in which we have computed three frequencies. One is FHI, the other is FH0, and the third one is F beta. This is F beta that we have derived the relationship for F beta. Here this is shown. So we are arrived at this point where we would now see what is gain bandwidth product. So gain bandwidth product is a figure of merit which basically relates gain of the amplifier with the expected operating range. So this is the response of the amplifier, in which these are the break frequencies. This is the lower cutoff frequency, and this one is the higher cutoff frequency, and this is the mid band gain of the amplifier. In this case it is 100, and this thing is the bandwidth is the higher cutoff frequency minus the lower cutoff frequency. So in this case the higher cutoff frequency is 1 megahertz, and the lower cutoff frequency is around 250 hertz. So 1 megahertz minus 250 hertz, which is approximately equal to 1 megahertz, is the bandwidth of the amplifier. So gain bandwidth product is nothing but gain and bandwidth, the product of gain and bandwidth. So this product basically signifies the relationship between gain and bandwidth. If you reduce the gain, the bandwidth of the amplifier is increased. So this product, gain bandwidth product, always remains constant for a given amplifier. So students, अगर हमारे पास एक पर्टिकुलर एम्पलीफायर है जिसका रिस्पांस इस तरह का एक बैंड पास रिस्पांस है, जिसमें कि उसका जो गेन है वो दोनों तरफ डिक्रीज कर रहा है एक कांस्टेंट रेट के साथ, एक स्ट्रेट लाइन को फॉलो कर रहा है दोनों साइड पे। लोअर साइड पे भी ग्रेजुअली डिक्रीज कर रहा है कांस्टेंट रेट के ऊपर विद स्लोप -20 dB, और हायर साइड के ऊपर भी कांस्टेंट रेट के ऊपर कांस्टेंट स्लोप के साथ डिक्रीज कर रहा है -20 dB पर डेकेड के साथ। तो अगर इस तरह का एम्पलीफायर का रिस्पांस होगा तो उस केस में जो ये जो प्रोडक्ट है गेन बैंडविड्थ प्रोडक्ट, ये हमेशा कांस्टेंट रहेगा। मतलब अगर आप गेन को कम करेंगे तो बैंडविड्थ आपके इंक्रीज करेंगे। सो गेन बैंडविड्थ प्रोडक्ट would always remain constant. So in this example, if the mid-band gain is 100 for this case, and if I reduce the gain from 100 to 10, then bandwidth would be increased from 1 to 10. So gain is reduced 10 times, bandwidth would increase 10 times. That is, if gain is reduced, bandwidth would increase. So the gain bandwidth product is equal to AV mid into bandwidth, where AV mid is this quantity and bandwidth is FH minus FL. bandwidth fH minus fL, which is approximately equal to fH. So gain bandwidth product would be equal to AV mid into fH. So for this example, gain bandwidth product would be equal to AV mid is 100 and bandwidth is 1 megahertz. Gain is AV mid is 100 and fH is equal to 1 megahertz. fH 1 megahertz, and that would be equal to 100 megahertz. So this product is 100 megahertz. Now at gain of 10, the bandwidth as shown in figure 9.53 is approximately equal to 10 megahertz. So this is figure 9.53. If gain is 10 now, then fH would become 10 megahertz. So gain bandwidth product would be 10 into 10 mega, which is 100 megahertz. So gain bandwidth product would remain constant. So in fact at any level of gain, the product of the two remains a constant. So अगर आप gain का कोई भी level लेंगे तो उसके accordingly जो bandwidth होगी वो basically उन दोनों का जो product होगा such that it would remain constant. So for example, if gain is equal to 1 and then bandwidth would be equal to ft as shown in figure 9.53. So if the gain is 1, if gain is 1, this is the horizontal axis where the gain is 0 dB, and 0 dB you know is corresponding to gain of 1. So in this at this axis the gain would be equal to 1. So the cutoff frequency would be equal to ft, which is called the unity gain frequency, which is 100 megahertz. So 1 into 100 megahertz is 100 mega. So with the gain of 1, with the gain of 1, the cutoff frequency would be 100. So 1 into 100 would be 100 megahertz. So the frequency ft is called the unity gain frequency, and it is always equal to the product of mid-band gain of the amplifier and the bandwidth at any level. So that is ft is equal to AV mid into 100. So ft is the unity gain frequency, which is in this case is 100 megahertz. So ft would be equal to gain into bandwidth, and it would always remain constant. That is 100. This is gain into bandwidth, which is 100. In this case it is also equal to 100. So this unity gain frequency would be equal to gain into bandwidth. The gain and bandwidth product would always remain constant, and it would be equal to ft. The gain and bandwidth would always remain constant and would be equal to ft, which is unity gain frequency. Same applies to transistor beta as well. This relationship holds, that is ft unity gain frequency would be equal to gain bandwidth. Gain is the mid-band value of the beta into the cutoff frequency f beta. It would always remain constant. So the general equation for HFE variation with frequency is defined by equation 960. This is equation 960, and for the amplifier it is defined by AV equal to AV mid over 1 plus JF over FH. So FH is the corner frequency or cutoff frequency, and this cutoff frequency into the mid-band gain is always equal to the unity gain frequency, as we have seen here. So this cutoff frequency and the mid-band gain is always equal to unity gain frequency. Note that in each case the frequency fH defines the corner frequency. Now substituting equation 962 for f beta in equation 965. This is 965, and the equation of f beta is this one, f beta. And if we plug the value of f beta here in this equation, then ft would be equal to HFE mid into f beta, where you can cancel these two, and you will get unity gain frequency is approximately equal to 1/2 pi Re into C pi plus Cu. So next we see example 9.14 of your book. In this example, use the network of figure 947. This is the circuit with the same parameters as in example 9.12. These are the component values for this circuit, and this is beta, which is equal to 100. With the addition of these parameters, these are the junction capacitances and the wiring capacitances. These are the wiring capacitances. With these parameters, determine the following quantities: FHI, FH0, find F beta and FT. At the end, in part C, sketch the frequency response for low and high frequency regions using results of example 9.12 and of this example part A and B. So in order to find out the cutoff frequencies FHI, FH0 and F beta, for these cutoff frequencies we have already derived the relationships of these cutoff frequencies from this circuit. These are the relationships of the cutoff frequencies FHI and FH0 and F beta. So we can use these relationships here. So FHI is this one, FH0 is this one, and this is F beta. And you can plug the values of these quantities R Thevenin I and Ci. R Thevenin I is nothing but Rs in parallel with R1 in parallel with R2 in parallel with beta Ra. So these values are given. You can plug these values to find out the value of R Thevenin I, and then you compute Ci, which is nothing but Cwi plus Cbe plus 1 minus Av into Cbc, where Av is the gain of the amplifier that we have already computed in example 9.12, and it is also shown here. So total, when you plug the values of Cwi and Cbe and this capacitance, you will end up with total input capacitance equal to 406 picofarad. Then the resulting higher cutoff frequency of input side would be equal to this much. Similarly, for FH0, you need to compute R Thevenin naught and C naught. This is R Thevenin naught, which is equal to RC in parallel with RN, and it comes out to be 1.419 kilo ohm, and C naught would be equal to output wiring capacitance and junction capacitance and output Miller capacitance. So you just plug these values of capacitances and the corresponding relationship of the Miller output capacitance. You end up with the C naught equal to 13.04 picofarad. So when you plug the values of R Thevenin naught, C naught in this equation, you will get the output cutoff frequency of 8.6 megahertz. So this is 687 kilohertz and this 8.6 megahertz. Lastly, for F beta, you have these quantities: beta mid, which is 100, Ra you have already computed in example 9.12, which is 15.76 ohm, and these two capacitances are given. So by plugging these values and after computing this equation, you will get F beta equal to 2.52 megahertz. You can also compute the value of unity gain frequency, which is nothing but beta mid into F beta. Beta mid is 100 and F beta is this much, and you will get Ft would be equal to 2.52 megahertz. So at the end, in part C, you can draw the response by looking at the corner frequencies. You can see FHI will determine the higher cutoff frequency and the bandwidth of the amplifier, because this is the lowest of the cutoff frequencies of high frequency response. So upper cutoff frequency is very close to approximately 600 kilohertz. So this is approximately equal to 600 kilohertz. So FHI is indicated here, approximately equal to 600 kilohertz. So this is 1 megahertz point. So first break would occur at this frequency. So this is the FH of the amplifier or F2 of the amplifier. This is the lower cutoff frequency FL or F1 of the amplifier. So this would be the bandwidth. The other cutoff frequencies are higher than FHI, for example F beta, which was around 2 megahertz, and this is FH0, which was around FH0 8 megahertz, 8.6 megahertz to be more precise. So this is 8.6 megahertz. So for each break frequency, the response drops at a constant rate, and the mid-band gain would start dropping when first cutoff occurs, and the response start decreasing at a rate of -6 dB per octave until the second break point. After the second break point, this roll-off starts doubling. So that's the solution of example 9.14. I hope it is now very much clear. So in the next class we would see chapter 9's the remaining topic, the last topic, and then we will move on to chapter 10, which is operational amplifiers. Thank you very much. Thanks.